Lobster Island, a hypothetical location, experienced a significant meteor impact on May 9, 2022, resulting in the release of radioactive material. As a result, the citizens were evacuated to ensure their safety. The radioactive nature of the meteor impact poses potential harm to both humans and the environment. The rehabilitation plan aims to restore the island to safe condition by reducing the radioactive contamination to an acceptable level of 350 parts per billion in the waterbed. In terms of the effect on Lobster Island, the radiation or the meteor impact has likely caused the dispersion of radioactive elements throughout the island's environment. Radioactive decay is a natural process in which unstable atomic nuclei release radiation. These emitted particles or electromagnetic wave can damage living organisms and their genetic material, potentially leading to radiation sickness, increased cancer risk to the human, and also genetic mutation to the plants. The extent of the impact and the specific isotope involved would need to be assessed to determine the potential long-term effects on the environment and human health.
As we were informed regarding the disaster a few months ago, is it possible for me to see the progress that you guys are currently working on?
We have listed out all the issues that the residents are facing at the moment.
For problem statement, firstly, what is one of the radioisotope in the meteor? Next, how long will it take for the amount of the radioisotope to decay by half? Next, what methods can be used to identify the radioisotope and time taken to reach the safe concentration level? Meanwhile, for the objective, first of all, identify the radioactive element in the meteor, compute the radioisotope's half-life. Next, analyze the decay rate kinetics, including derivation of integrated rate law, and last but not least, determine the suitable date for rehabilitation of the island.
Radioactive decay is considered as a first-order process because the rate of decay of a radioactive substance is directly proportional to the number of radioactive atoms present. To get the first-order rate law of the equation, we can derive the integrated proper rate law equation for such reaction as follows. This is the original rate law equation. Then we can rearrange the equation by putting all A variables at one side and replace the dt to the right hand side. Then integrate both sides. This is the equation after the integration. And then simplify the equation, become ln A at time t minus ln A at time 0 equal to negative kt. And as we want to prove that this is the first rate order, we can rearrange the equation again, become a linear form of the equation, becoming ln A at time t equal to negative kt plus ln A at time.
Alright, so after we concluded the equations that need to be used in this experiment, I'm going to show you what we have got from the experiment that we conduct for the past 64 days.
For the past 64 days of experiment, we managed to identify the initial concentration of radioactive substance that we are currently studying on, which is thorium-232 at 1.3% weight on the first day. Assuming the water taken for the experiment is 1 liter, therefore the mass of thorium-232 that consists in 1 liter of water is 13 gram. By calculating its number of mole, we were able to spot the initial concentration in unit of molar at 5.60 T times 10 to the power of negative 2 molar at day 1.
Okay, so we have conducted a graphical analysis, and this is the half-life. So this is the first order reaction graph.
After we tabulated the experimental data of radioactive concentrations, we conducted a proper graphical analysis. The integrated rate law for each common type of reaction can be plotted as a straight line. So we have to determine which order of reaction is the radioactive decay of thorium-232 in order for us to proceed with our calculations. Firstly, we used 0th order reaction and plotted a concentration of thorium-232 against time graph according to the tabulate data. Because the plot of concentration of thorium-232 against time is not a straight line, we know the reaction is not in zeroth order. Hence, we attempted the first order reaction graph, in which we plotted a natural logarithm, log concentration of thorium-232 against time graph. From the graph, we obtained a straight line with a slope of negative k. In other words, the rate is directly proportional to the reactant concentration. This means that the radioactive decay of thorium-232 is a first-order reaction.
Then, we use the first order reaction of equation to calculate the K constant using the formula of ln AT equal to negative KT plus ln A0, assuming A as the symbol of thorium-232. Using the value of concentration of the sample that we take every 21 days for the value of T in the equation, we then substitute AT with the concentration of day 43 at 1.408 times 10 to the power of negative 2 molar and A0 with its initial concentration at 5.603 times 10 to the power of negative 2 molar. Eventually, we will get the value of constant K at 0.031 day to the power of negative 1.
So from the K value obtained here, we can calculate for T half-life. Half-life of thorium-232 equals to ln 2 over K. We plug in the value of K obtained, which is 0.0321 per unit day. We will get half-life equals to 21.59 days. Next, we express the initial concentration from the unit of parts per billion ppb to molar. We assume that the mass of solution is 1 kg. By using the formula for ppb, we can obtain the mass of solute, which is 350 times 10 to the power of negative 3 gram. By using molar equals to number of mole over volume, we will get 1.508 times 10 to the power of negative 3 molar. After obtaining the rate constant and initial concentration in molar, we can calculate time to reach safe level by using T equals to negative 1 over K ln concentration at time T over initial concentration, which is 112.62 days or 3.754 months. So the date for rehabilitation is on 29 August 2022. And that concludes our research.
Ladies and gentlemen, today is a momentous day as we gather here to celebrate the reopening of our beloved island, free from the threat of radioactive materials that once plagued us. The journey to this day has been one filled with challenges and uncertainty. The arrival of the meteorite brought with it not only wonder but also danger that tested our resolve. The radioactive material that it carried, which confirmed was thorium-232, posed a significant risk to our environment, our health, and our very way of life. Yet, through unity and unwavering efforts, we have successfully conquered this threat. I would like to express my heartfelt appreciation to the scientists and experts who worked tirelessly to understand the nature of the radioactive materials and devise a safe and efficient plan for their removal. After thorough daily observation, they have confirmed that half-life of the element is around 21 days, and after 3.75 months of research, it was confirmed that previously on the 29th of August, the island is once again safe for residential. With the opening of our island, we have a unique opportunity to rebuild and grow. We will implement robust monitoring system and safety protocol to ensure the continued well-being of our residents. The lesson we have learned from this experience will guide us in building a more resilient future. We will invest in state-of-the-art early warning systems and emergency response infrastructures to ensure we are prepared for any future challenges that we may pose. Thank you all for being here today, and let us celebrate the reopening of our island with pride and joy. Together, we will build a brighter future for all. Thank you.